Welcome back. And now we are going to have the last lecture by Marko Stosic from the Technical University of Lisbon. Oh, and Serbian Academy of Sciences, right?
Mathematical Institute.
Oh, sorry.
Brotherly Institute. The local. Well, first, thanks again, and thanks for everyone for surviving and even returning from lunch. It's been a demanding week with too many talks, but I guess it's been interesting, hopefully, for everyone. So, you know, when you're in a school, then students didn't have class for many days, so you usually start with, well, testing the memory. So my question is, instead of me repeating what was on Monday, does anyone remember any of the pictures from the last time? So, for example, this thing, what was this? Well, not counting my artistic skills, modern paintings. So this was the diagram of the, well, not the diagram, but anyway, it represents the triply graded homology of the trefoil. And details doesn't matter, but for example, that guy, trefoil has a homology which is three-dimensional, and there are some. It comes with a bunch of differentials. So there was this big square commute. So this is this guy, triply graded theory here, and it comes with a bunch of differentials on itself. So it's not just homology theory, again well defined, but it also comes with a collection of differentials. In fact, infinitely many. So basically, well, one for any integer n for now, but well, a priori a lot of them. So such that the homology of this triply graded with respect to this extra leads you to the SLN specializations. So some doubly graded homology, and well, these are very special cases like SL1. Usually, you always can pair everything with respect to this D1, so that you go to SL1, which is a trivial one. But it should work in general. So that's the goal. And what is that categorification? That is that lift that we wanted, that lifts this relationship between conflict PT polynomial. So this is a two-variable polynomial you all love and cherish, and this is its categorification, and its specialization is, well, let's say SLN specialization. This big theory with some history, and so we can, in some sense, collect within this picture, within this diagram. So, what's the next question? So the next question is, so, well, you said that you remembered this and this. Unfortunately, who was at Sergei's talk, you know that he was giving presents. I don't have any presents. It's moral satisfaction for you. So my question is, who remembers what was this? What was this on Monday?
The second homology.
Ah, good, but you're cheating, and so you were not observing, so we never mentioned this on Monday, so this is no prize for you. So the point is that what we did last time, and this is what we mentioned, well, I was hoping last time to get to this part, but last time everything was for the representation, so color were just fundamental representation, there were no colors, as Sergei would like to say. That is the only thing that should matter. So we should put colors here somewhere, and well, because only 45 minutes, I will not go in details, but all these polynomials, well, we always start with the polynomials, so everything else is just build up or our invention, but the polynomials exist not just for fundamental, there are other ones, so like there was a Jones, there is also something which is a Jones polynomial, but I'll try to write it like that, so, and then put something like Vn, where Vn is n-dimensional irreducible representation. For example, well, this can be also written as n minus first symmetric representation of the fundamental one. It doesn't matter. The point is that these polynomials, for example, exist, and well, these are again famous, and they're called Color-Jones polynomials. Yeah, again, of course, there are polynomials so for any group and any representation, but I mean, I stick only to SLN first of all, and then all representation will be either symmetric or anti-symmetric. So will not go in the highest possible generality, but this is already quite a lot. So these are, I don't know if I have some name, a little bit cheating, but let's call them J and Q. So for example, again for the trefoil, so for our again favorite one, so one can say that J1, which is like one-dimensional polynomial, is just one. J2, and that's fundamental, so two-dimensional representation, that is a Jones polynomial, and that's the one we discussed. And so we remember even the homology is three-dimensional, but the polynomial has three terms. And now I will not write, it takes a lot of time, but J3 of Q, yeah, of course, they're still, everything is still polynomial with integer coefficients. Again, I suppose, hope that you all went to Sergey's talk and listened very carefully. What we like very much, we want to have integral coefficients, and luckily knots are much more simpler than these three manifolds, so here we are naturally in this world. So anyway, this will be some polynomial. Well, I'll just say that it has 7 terms, in the sense that 7 summons. Who wants, you can play. And also they're purely combinatorial. Maybe Joseph will come tomorrow to that point. So there are these Kaufman brackets and everything, but these polynomials are, again, easily defined combinatorially. So, for example, this J3, so this second, which is second symmetric, it is obtained if we have a knot. So if you have some knot, we just, now it will be better not to draw, but you just take a cable, so you have a knot and you make a copy of it, not by itself, and put something that's Jones-Wenzel projector. And then for this thing, you just compute Kaufman bracket or however it goes. So it's just computationally more complicated because you have to use cables, but it is very closely related to that thing. So these are perfectly well defined. And there is one extra thing for Cauchy-Jones polynomial, which is in fact in background of all this, but again, I will not say that much, is that so we have a collection of these polynomials. So one for every n. So these are these Cauchy-Jones, for example. It will hold for every. Although we have infinitely many a priori, and they grow pretty much, they are in fact all related, and there is a recursion relation. So there exists, and it in fact exists for every knot. There exists something. Well, maybe like this. So there is there exists some number k. It's a fixed number, but for every knot, of course, but such that j n plus j r plus k, usually not colors of r, and there's some coefficient plus ak minus 1 some space. That's a0 jr is 0. So there always exists a recursion, finite recursion relation with slight trick. So the coefficients, so which should hold for every r. The coefficients in general, like in Fibonacci sequence, doesn't depend on your r, but here there is a dependence, but it's very simple. It's just a polynomial in q to the power r. So there is something like some polynomial. You can write this as some finite differential, finite recursion relation. Usually it's called holomorphicity. So basically, it exists for every knot. I will not go into details, but usually that gives rise quite simply, but it's very nice, to operators a hat and some a polynomial. So there is a very fancy stuff coming out of it, and although I will not mention it, it is somewhere in behind. Well, that is what's going on behind all this. Of course, and if you now fast forward everything, so this was for the Cauchy-Jones. So for SL2, you can of course change here to SLM if you want, and you can in such a way then for every representation. And well, again, I said You can define for every representation, but let's say symmetric one, for example, two variable version, so you can put like this. So I'll put here any representation. So for any representation of SLN, you can define the polynomial. You can collect it in a two variable one, which specializes in the same way. I should use the other color. We already have red. It's a blue. So that's the. And then what will happen? So we are in the same world. So again, ideally, everything should come with other colors. So this should go for all colors. What we like very much and which we understand the best is in the case when R is equal to sim R, so symmetric representation, or if you want, prefer for some applications are anti-symmetric. And all these things work, so then in principle, what we compute, you get it the same way here, as Piotr said well, so you're not grounded because you know things, so this is second symmetric one, but like this way. So this is second symmetric of the trefoil. So it turns out it's 9-dimensional in the same way as we obtained this diagram. And there is an extra, so you see here some differentials which go in the same way. Here there are much more of them, so here I draw 4 different differentials. And so in the same way as before, so there are 2 of them, so there are 2 different differentials such that the homology of this doubly graded one is second symmetric. So I will not write which are these, but there are 2 different differentials. I think the colors here are so this is this red one, but also the other guy, the blue one, which goes now 2 steps to the left. But they are both cancelling, so this is something 1-dimensional. Or in other words, like above, this. So for example, these 2 guys pair up, these 2 pair up, these 2 pair up, so you're left only with this thing in a homology. But there is also something else, and I mentioned maybe at the last time, is that now imagine this. It's like a fixed, like a photo of some image. So we have here this picture for this particular representation, let's say for second symmetric, but we also have for the ordinary one. And so not just that they are in their own world, but it's like they interact between themselves, and it's related to the representation theory. So representations. The same representations for different groups might be isomorphic, and then it leads to the maps between the 2 of them, or between different this leads to different differentials. For example, there are differentials that go from the second symmetric, so differentials, I will go with this one, which takes you not something trivial, but to something that is isomorphic to the, well, let's say ordinary, so first symmetric. And in this case, there are differentials indeed. For example, there is this blue one. No, this dashed. I think I wrote with dashed. So there is something going very weird. So this has something to do with SL3. And there is also, oh, I haven't mentioned. So here, this guy paired these 2 guys. So these 2 get cancelled. These 2 get cancelled. These 2 get cancelled. So the homology is generated by, this remaining homology is generated by these 3 generators, which are more or less the same, isomorphic to these guys. So this is what this says, and this is predicted for all knots. And finally, the same thing for there is this vertical differential, which is now not HFK as we had before, but just again some pairing. Again, I'm not going much in details. There are so many different properties of this. It's much richer because now we have for every color, and they can play with each other. If you remember last time, I also put a long list of properties of these homologies. So this time here, more or less the same holds, even more. But there is one property that so it was observed first, but now it's a theorem. And I'm not sure, well, if it's the right theorem or not, so later proved, but it's called exponential growth property. It's maybe the most relevant for the last part. So it is how it is related. So how the size, when you increase color or symmetric powers, how the size increase. First of a polynomial and later as a homology in a homological world. So here we could see there were 3 terms and then 7. However, here, well, this is a very naive way, of course, we're doing, but you can see that here the dimension of this guy was 3, and dimension of all this, of the big homology, triply graded, was 9. So, as a good mathematician or good physicist, especially an experimental one, you can easily conclude what's the next term. And in the case of trefoil and many, many knots, it turns out that the art symmetric, or to that matter anti-symmetric, where there is symmetry, looks almost, well, very close, well, I'm not to the ordinary one, then tensor pair times. So, as written, this is not a theorem, but this looks to hold for, this seems to hold for all, well, for many, many knots. However, what really holds for sure is that there is a spectral sequence starting at this guy, or maybe there's some differential spectral sequence tending to this guy here. So in some sense, so spectral sequence, these are like homology. So let's say this homology certainly includes this plus something more. And well, there is this thing that this spectral sequence, well, now that part is not very precise, quickly collapses. Meaning that frequently these two guys are isomorphic. And so more or less, morally what you can see here is indeed where this very, very small example is what happens. So if you have 3 here, and so even you can do it row by row. So there are 2 and 1, and then there are 4, 4, 1. So it follows that that pattern. And there are a lot of cancellations. For example, if you go to polynomials, you see here that there are 7 terms. You don't see this 9. So well, it doesn't matter which one these are, but these are these 2 guys. When you specify a equal q squared, they got killed. So in some way, some sense, only this triply graded theory, this turns to hold. By the way, this is, well, this as a spectral sequence is due to Jake Rasmussen and Paul Wedrich. So this was predicted before, but well, maybe not in full generality, but like this. Well, I don't have too much time, so I'll not say too much more about this. So in some sense, symmetric ones, you need something else, you need some extra data, and we'll now, the final piece of my trilogy would be about this data that is required, how to go from the, how to collect all of this and what is the symmetry. And so finally, we go to the third part, or second. It's not Squeever's correspondence, or at least in a way that I want to present. And now I had a different idea how to present, but maybe I'll just write in this way. So I know some of them you are survivors from the Friday, so maybe you, well, and probably you saw it many times, but I'll write it in a different way. So well, maybe I won't. So here I said a lot about homology. So again, unlike three manifold homologies, which are in many cases, well, in majority of cases not defined but only hoped for, here knots are much simpler. Everything, well, almost everything is even defined, and we know many, many properties, so we can even prove a lot of this stuff. So we are in a good position. But nevertheless, if you go back to polynomials, so now I'll go back to PR of AQ. So these are symmetric colored Horn-Flip PT polynomials, so no homology for now. And what Squeever's correspondence effectively says is that, so I put here reduced just to be nicer formula. So just not to make mistake, is that PR of AQ, so that for any Q, for any knot, one can rewrite this PR of AQ, so that for every R, for every this color, this can be written as a huge sum. Well, over some indices, so well, also not R. So K can be arbitrary, so that the sum of di is equal to R, to this index, and then there is a minus Q, but that doesn't matter, and then there is a sum ij, Cij, di, dj, so there is a quadratic form in di, dj, and then there are some linear terms which are linear, which are linear in D. And also we have other variable A, also linear in D. Relevant. And times, maybe, is it just product of few cohammers? So essentially, knot-Squeever's correspondence says that for any knot, there exists matrix C, which is K by K, symmetric integral matrix. So this is the most explicit form, at least in a way how we, in all, wherever we have managed to prove it, it was basically proved in this form or something of this kind. And now the most important question, because this is school, so I ask you some 3 questions at the beginning, which are completely relevant, you can completely forget. But what's the most important thing? Well, one of the most important things in this school was Sergei's lectures. So I'm very happy that he put some formula like this yesterday. And I think miraculously, I don't know why, but I mean, I would like to say that this is very related, but I think it was not discovered in the same way, but this is exactly the same form. So all these characters of VOA and 3 manifold invariants, or any possible relationship with any kind of weird characters or some formulas was somehow it turns out to be related to this object, where you all the information about some invariants, well, in this case not invariant, you transform simply in a quadratic form, or some small symmetric matrix. And again, here there are also many problems. So for example, even when this exists, this matrix C is not unique. So there are not issues, but interesting problems. If this matrix C is not unique, so one question is there something else apart from just this definition? So is there some natural structure in all this which will tell you what is DC, or what would be the most relevant ones? And also the ways why this works at all. So even though it's more or less of the similar time origin of this, or at least our goal was completely different. So it was related to the representation theory of quivers. And I believe if anyone was here in March, I think Marko was here. I suppose that he was speaking more about this side.
Yeah, and there will be a lecture series by Vladimir Butsenko.
Oh, even better. So who likes to learn? There are many, very nice things about this. So quivers are just, so again we have some graphs, but these are graphs corresponding, which are determined by this matrix C. So quivers, so if we have a matrix, so this matrix C, well, it is again an adjacency matrix, but slightly different. So if we have a graph with some vertices, okay, we here want to be symmetric quiver, so in our case, but which means that no matter how many arrows are from one vertex to the other one, there should be the same number of arrows going the other direction. There can be loops. And then, for example, for this graph or quiver, which is just a directed graph for us, well, one associates, well, each vertex has some numbers, so this is 1, this is 2, this is 3. And then at position ij, you write how many arrows are from I to j. So from 1 to 1 is 0, 2 to 2 is 0, 3 to 3, 1. symmetric. Oh, this is a little bit maybe dumb quiver that I wrote, but also we want to. So for us, at least, what we thought is that it is related to this, to these quivers. So what Sergey was saying yesterday has a priori nothing to do with this. It was completely some other different invariant, three-manifold invariant, which again is obtained by surgery over knots, but it's slightly different. Some history. So he mentioned yesterday that. So I think he was speaking all the time about z hat of three manifolds, but. It started with closed, but this can work also for manifolds with torus boundary. And in such a case, you can define for a given knot, you can define well, this z hat invariant of a knot complement, which is a three manifold with the torus boundary. Now this is usually called Fk. And turns out, well, as it was pointed yesterday, so this naturally has the form of a, this z hat naturally has a form of a series, unless we here with polynomials. However, so there is an analog, so this Fk is not invariant, which is somehow, well, I'm not sure if it's really related, but somehow through this series, and it has this similar form, so somehow this is one of the rules. This Fk can be also written as quiver form. So this is some form where we have some sum of these forms, so something like q to some quadratic power and times this q cohammers. Select the time. So I would like keep this here. Again, to resume, I would certainly encourage every one of you to work on three manifold invariants, and well, knots and three manifold invariants, because these are really now exciting topics, something is new. But what is nicer and easier for knots is that, again, all these invariants are much easier to define and very well known. Everything is naturally defined for every Q. There are no these problems whether it's generic or non-generic, and there is also homology over it. And so just to end with this brief part is, as I said here, in this definition, it's how it came in, was that this is purely polynomial thing. There is no homology. However, well, one can do this again for this for this same trefoil. One knows that it's computable variable polynomials, and you can blah blah blah. You can do this mumbo jumbo, and you can get this matrix C, and it turns out to be a 3 by 3 matrix. And I write it. Well, it's even similar to what I wrote before. Example again. And well, you can probably recognize some familiar things. So, as I said, this matrix works. Also, there are others, and there is a huge non-uniqueness. It's very infinitely many of them, which will give you again the same answer. But this is, in some sense, the most natural. So, what is the most natural here? The most natural thing is that the number, so the size, if this matrix is 3 by 3, and 3 is exactly the dimension. Well, in this case, it's a lot of stuff, but 3 is the dimension of the homology. Trefoil. And not just that, but it turns out somehow the elements on diagonal, I purposefully didn't erase the diagram, so the degrees, the terms on diagonal are precisely, so maybe I'll put CII, is the this homological degree, 0, 2, and 3, this homological degree, well, this is more of an observation, but the degree of the generator, well, corresponding, because there is some one-to-one correspondence, it seems so, between the elements of homology and the vertices of the nodes of the quiver. Of the generator corresponding to vertex I. Well, of course, there is the question of off-diagonal, but at least this fixes in some sense the size, or at least it bounds. There is this also issue that Sergei was mentioning, even in the case of three manifolds, if you want to bound, well, it seems that the smallest possible C is the right choice, the best choice. In this case, it seems to be very much bounded by this homology, by the homology groups. There is also a question of the off-diagonal entries, and in some sense they, well, as we said, so this homology is isomorphic to this here, so tensor product of this guy with this, but it doesn't fix this Q gradient, so in some sense it stretches it. These off-diagonal entries, in some sense, they measure this stretching, so it would be nice to see that directly in homology. So again, even here there are a lot of things to be done, but maybe not to say that everything is negative, so positive things are this not squivers correspondence has been proved, or better said, even computed for many knots, for, well, for many groups, so for rational ones. Yesterday we discussed the naming, I think it's arborescent are the correct, but includes others, so and many others, torus. So for some of them it's done explicitly, so you can compute even the whole matrix C, and for some, at least in principle, you know that this holds. So, how to say? In some sense, I think there is something deeper philosophical, which we stumbled upon this more or less experimentally, but it turns out that its expressions of this type are very, very, very relevant in all this story. And so there is much more insight to understand, and part of it seems that these homologies are key steps. As you can see, there are no homologies in this definition. Nevertheless, they're present. Maybe I want to show a couple of slides, maybe at the end. So it's maybe just to say why it's not squivers correspondence. So one way is, instead of, so you have these PRs, usually it's written, so this Fk is a series, so the way how a series enters here is that this Px is defined one series with some dummy variable n, which is, R, sorry. So when you simply sum over all invariants, usual stuff when you don't know what to do. With a collection of invariants, you just collect them somehow, and this basically says that, so this question says that you can write P of x as certain sum corresponding to some quiver or some matrix, which now depends on as many variables as quivers. So this K I have here. And the only thing is that these variables xi should be set to something, well, a to something, so something linear, so some coefficient doesn't matter, but to x. So I will not go in details. And this is this, well, in the quivers case, this is quivers generating series, but this is essentially this sum of this form. The reason why it's written here in this way is because then not generating, so generating series for quivers, which is natural thing there, is naturally related to some series because PRs are polynomials, but series are natural, and that way this Fk or Z hat also enters because they're naturally series. So we can naturally associate them to series in that case, a quiver generic series. There's only one final step, and the recent one is, you can see that here there are some linear terms or there can be some numbers, and here is always one, at least in our original world. Now for fk, you can do the same story. For fk, it is automatically, it's natural, or it shows up, it's natural to have variables xi going to x to some power, and I can be some can go to x, some can go to x squared, some to x cubed. Well, simply the nature is saying that. And so I think the generalized, so the right way for not square correspondence is also why couldn't we put here some numbers and I? And the only difference that would make in this here is that here we had 1, so it can be written as here we have some number n i's, which are i's from n, even 0 or 5. Not 0 in this setting, but so maybe the right, this is the right not square correspondence. So ideally, I think that would be ideal to prove that it holds in general, and maybe, if possible, through this more general stuff using but these homologies and all these pictures and diagrams, like, well, which I draw nicer, nice time, and this time so and so. Well, this is the big picture, and well, big hope. Of course, picture is still below the ones for the 3 manifolds, because here again I say we're in a much better situation, but this is obviously how the things are going on, that all the things are quite related. Well, should be very related one to each other. 2, right? Yes. So I have in the title combinatorics, and I cannot write really nice. I would like, this is just, well, I'll say, so I'll try to show make a couple of slides. And so this is corollaries, or maybe I would say benefits of not square correspondence is that, so some of the benefits, well, one that we didn't anticipate, but it is related, is that we have some series here in one variable, and here if we have series in many variables, and there is a way what to do with them. But in some sense, this allows for stratification, so one can, well, count this by using this. So it's very useful to refine, in some sense, to refine polynomial, not invariants or some numbers that show up. In particular, BPS numbers show up. So for physicists, I don't definitely have time to show. But I will now try to show just some things that come up out of it in the particular case of torus knots. And as Piotr told me, I'll try to be projector now. This one? This one. So this will save you from my drawings. Not everything you can just forward. Blah, blah, blah. So first of the pictures. So, oh, it's quick. Okay. Okay, this I showed you. Oh, okay. So this is the right thing. So this is in flat space where everything is flat. This is in curved space. Right? No curved, but this is the point is that this is very.
And this is
okay.
clicker.
Well, this is just to repeat this thing, that there is a lot of things in homology which you don't see on polynomials. And, well, doesn't need to be colorful, but the point is there is a lot of rigidity in all this. And again, I mean, this is more to emphasize. Again, I apologize for home fleet. This is copied from somewhere. This shouldn't be. This is very old, sorry. But the point is, this was for other stuff. Okay, it has to do with this counting of paths. So this just to, maybe who hasn't seen this, is this a priori has nothing to do with knots and everything, but the counting of paths, this is this question of, whoops, how it's going this way. So we have some critical line, which is like in this case with some slope, 1/4, and we want to count lattice paths in the usual way, so paths which go at each step either to the right or up, and you want to count how many of them are going from here to, say, second point. And that clearly depends, of course, on the slope of this line. and many other stuff. You can also count with some weight, with this, where the weight is the area of this, between the critical line and our line. This is purely combinatorial problem, nothing to do with this. How he enters, it's not that mysterious, but it's mysterious why it's so nice. Well, equivalent, this is just equivalent formulation. You can also count how many steps are like, if you go up, you go by 1 and down by 2. So there are different interpretations, but I'll stick to this one. And somehow this colored conflict PT polynomials, well, at least, well, coupled with quivers, you have to do something with this counting. In particular, well, okay, this is generating series. The point is, when you want to extract something, you find this quotient that describes somehow asymptotics. And I mean, I care only about classical limits, so you can. Well, this is something that mixes all colored polynomials, but in a very useful way. Again, this pk of q, these are these, and you can write it in a nice way, and somehow you can get some coefficients. And the point that these coefficients are somehow stratified now naturally through quivers that correspond to this knot. So now there are a couple of steps, but the point is, if you take, so I said you want a critical line of some slope, and okay, here there was, what happens here, sorry? So there was some rational slope. Exactly, you take that rational slope and take that torus knot in the right framing. So there are some technical details. Find this quotient, and well, out of it you can extract these numbers an. How? Well, I'll skip many details, but here, for example, for torus 2, 3 knot, you can find, well, quiver, just part of it. So this is relevant part of a quiver, and from this quiver you can just read off the formula. So there are some numbers 7, 5, 5, 5 in this framing, and you put them in the right way, and you get some formula which is this turns out to be a very famous combinatorial formula, although we didn't even know. But the point is that there is a count. This is explicit formula for an, which is stratified, so it's written as a sum of integers, although it's not obvious these all numbers are integers. Or maybe here it's the nice way. So the number of paths are diagonal sums, but they naturally simplify within these numbers, and these numbers are can simply be read off. They depend on the quiver, which in this case is 2 by 2. And the quiver is that one that corresponds to a torus knot. So there are a couple of steps, but the bottom line is simply torus knots through this correspondence give rise precisely to these numbers. Here I lied a bit. So here in this case we didn't have A, so we just use part, or maybe not the whole homology, not the whole polynomial, but just this one with the lowest A degree. So that is why there were 2 generators. So the quiver was 2 by 2, but you can also put everything. Okay, here this is some fancy examples. Blah blah doesn't matter. Oh, even worse. But the point is, this may be the right one to finish. Although still now it's been updated. When you input all this A and diagonal, so this parameter A, it is when you generalize instead of these lattice paths, when you count these so-called Schroeder paths, where you also allow diagonal steps. So you can go to the right, up, and diagonally. And now when you count, well, it's a little bit again, blah, blah. And there is something with specialization of variables, but you can see here that it's still going to X. Here A kicks in. It turns out that you get this series, well, this quotient. This is purely depending, again, on a quiver. You can get, some series in X. You have also parameters A and Q. And it turns out that all these terms count something. For example, if you go from 0, 0 to this point, it counts all Schroeder paths. So powers of A count the number of diagonal steps. So for example, A squared, there is one term with 2 diagonal steps. Then I don't know, well, choose your favorite one, but I don't know, for example, this. There are 3, so there is some AQ cubed. I guess this is this one. It has 1 diagonal path. The power of Q is the area of this, whatever we're seeing here, and there was some X, so X square meaning that we go from this is like the second point on this diagonal, so it's 0, 1, 2, second point on the diagonal. So the 3 parameters of the paths of the counts are naturally encoded in Q, in A, which are the parameters, exactly of conflict polynomial, and X. And well, I not have definitely more time and about the finish. So this was for very diagonal ones. So this corresponds in fact just to the unknot. Although I tricked you a little bit. So this is a framed unknot and it all counts all Schroeder paths, but this can be extended even for all torus knots and these generalized paths under lines of rational slope. So, which is something that Piotr Sulkowski and I have been doing, and I think even today maybe finally will be out on the archive. So it includes mixture of everything. So definitely not to think about it anymore, right? I maybe better not to promise, but today or tomorrow. So this is, well, somehow in some sense encompasses that this is old story, but all this, somehow the conflict polynomials through these quivers naturally count them, plus you can also see, so, okay, this is the advertisement without a picture. Well, I guess that's it, so I'll try to skip forward, though there are Z-hets, never mind. So, thank you for attention and for surviving all 3 lectures, right, this week.
Thank you.
Thank you.
Questions?
Do you expect this connection to lattice path counting to be special for torus knots, or be analyzed to?
Great question. So it seems so that it is so special for torus knots. So that's part of a surprise that it is such a simple and such explicitly. So for others it's tricky. So for others, because this has to do with count of PPS numbers, there should be combinatorial expressions, but well, we haven't found any yet. I think goal of this is just to impress and say that this is very nice, but this means that there should be combinatorial expressions, but not as nice as this. But you could get combinatorial counts for all knots, of course. For now, this is either ongoing work or ongoing thought. How this will be.
Maybe I can add that in old paper with Piotr, when I was his PhD student, we wrote about some combinatorial constructions for different knots, although in some simplified cases, based on extremal, so the extremal A polynomials. So extremal means the highest and lowest powers of A. And I mean, this extremalization is due to simplification, then it is possible to have some control over it. But there we had also similar combinatorial constructions.
So maybe just to put some words. So when these are blah 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 blah. So we have this polynomial y. You define this series. I think now. So these numbers an, these coefficients are these combinatorial objects that we count, and they're collected in this series. So this y and x, they satisfy this is algebraic function which satisfies an algebraic equation, which is exactly the A polynomial that I mentioned, which governs the recursion relation of colored polynomials which exist. So these y's play in the background. So the only thing that happens for torus knot in particular is that, well, it's relatively simple. There is a nice combinatorial interpretation. So this combinatorics, so as I said, behind all this are A polynomials on one hand, and on the other homologies, well, which we understand partially, but not very well. So unlike Z-hat, we know more, but we don't know explicitly exactly how they are mixed.
What do you expect from generalization of the correspondence to non-symmetric diagrams?
Well, it should be just a little bit more complicated. So I think there are versions. I think Stosic did, right? For others, I'm not so sure. Maybe it's not as nice, but this was all built to understand LMOV conjecture. So in principle, should work for all. But I think we haven't done, or we haven't been working. So for now, symmetric ones are D ones, or only antisymmetric ones. But it should work. Well, there should be some nice extension. Happy to know more about it.
All the questions?
one historical comment, as I should do so. So Schroeder number is the only obvious object considered by ancient Greeks or Romans. Probably you know that otherwise we don't have any proof that they did serious combinatorics, but here we have. And second is question to you, how old is the Duchamp paper? The paper about counting paths when you have given slope.
So I saw it in a paper which is from the early 2000s, so I think it's
So
1990s.
there are two books already, counting number of values, paths with various combinatorial situation, both are written by Indian in Canada, so it's good to check.
I'm not 100% sure, but I think it's not too old. I mean, it's something, I think 90s.
Well, these books which I know are from 70s, so older.
So, I mean, of course, there are different formulas, but I think this, well, Duchamp is only for 2-3. For example, we produced some weird formulas, but which follow from quivers, something like this plus this. So this is for 3-4 slope. So, but this comes automatical from, this is just from, so the only thing you need to know is the quiver, so it's completely different. But the point is that it matches, in the case of Duchamp, it matches these formulas, so I think combinatorially the goal is, there are different formulas, you can write this as some sums, but it involves either rational numbers or even complex numbers, and this is very nice analytic combinatorics. But this, and this was the original Duchamp, which is written, I think, in this way, that is sum over integers.
It's a special case of this general formula, we have various lines with various...
Yeah, of course, yeah. So, I mean, again, I love combinatorics, of course. I'm happy to see it, but this was not definitely our goal. This is just a byproduct. So we were very happy that we got, for example, in this case, something that's exactly Duchamp forms. This is what spits out from the quivers, and well, once you change the variables, it's exactly the formula. So yeah, I guess we are did something more than ancient Greeks if we are still in Schroeder numbers, but yeah, it's great to keep work going. Thanks.
Other questions? Okay, so let's thank Marko for the whole series.